So in this episode, we're going to talk about how to determine if we're doing a left, right, or two-tailed hypothesis test. And to do that, we got to start by talking about what do we mean by each of those terms. A left-tailed hypothesis test simply means that the p-value is the probability of getting a value that is smaller or to the left of your test statistic. A right-tailed test means that the p-value is the probability of getting a value that's larger or to the right of your test statistic. And a two-tailed test means that the p-value is the probability of getting a value that's farther away from the center of your distribution than your test statistic is. As you see, left, right, two-tailed is really just a description of where the p-value is on the graph. So to figure out where the p-value is, we have to know what the p-value is. So let's talk about the definition. So the definition we are using is that the p-value is the probability of getting our data or more convincing data, assuming the null is true. Okay, so our data just means whatever you see in the sample. More convincing data is data that would better support the alternative hypothesis than the data or sample that you have. Okay, because remember, the alternative hypothesis is always what you're trying to prove true. So a couple of examples of what I mean by more convincing data. So it depends on what we're trying to be convinced of. So if we're trying to be convinced that the mean of an entire population, mu, is greater than 100, in our sample mean x bar needs to be much greater than 100. If we're trying to be convinced that the proportion or probability of something happening is less than 0.2, when we look at our sample proportion, p hat, needs to be much smaller than 0.2. And finally, if I'm going to be convinced that the standard deviation of an entire population is not equal to 9, I need evidence that says 9 is the wrong number. So I need my sample standard deviation S to either be much smaller than 9 or much greater than 9. So this is what we mean by more convincing data. Now, let's look at the p-value definition one more time, because there's a key element here we have to understand. So there's really three parts to this definition. It's probably getting our data or more convincing data, assuming the null hypothesis is true. Okay, so we need to handle all three parts now. The probably getting our data and the assuming the null is true, those two parts are handled when you calculate the test statistic. Right? You plug in whatever numbers you have from your sample, that takes care of the getting our data. Whatever the null hypothesis says, mu equals 100, sigma equals 9, that goes into the mix in our test statistic. So those two pieces are accounted for when we do the number crunching. So what does that leave us with? That leaves us with this more convincing data. Okay? And that is what's going to ultimately determine what is a left, a right, or two-tailed test. It depends on, at least to begin with, what more convincing data is. To figure out if you're doing a left, right, or two-tailed test is a two-step process. So it begins with what more convincing data is. So in every situation, whatever it is you're trying to prove, you have to figure out what would I need to see in my sample to convince me that the alternative hypothesis is true. So more convincing data depends on what the alternative hypothesis is. Now, here's where people get in trouble. Way too often, people want to stop there. If I'm trying to prove something is big, then it must be right tail. If I'm trying to prove something is small, it must be left tail. And that's not always the case. So we start off by deciding what specifically do I need to see in my sample to convince me my theory is true. We need a big p hat, a small x bar, whatever the situation calls for. But then the second step, right? The second step is to look at the test statistic. Right? We have to say, if we were to get our more convincing data, what impact would that have on the value of the test statistic? So we have a sample value, we plug all those in and we get a test statistic. So more convincing data then equates to, right, a more convincing test statistic. And that is going to depend also on the equation you're using. So don't forget to look at the equation. So let's look at several examples to see this in action. In our first example, the theory that we're going to test is that sigma is greater than 125. That is, our standard deviation for the entire population is higher than 125. First thing we would do is assume that sigma is 125 until we see some proof. Now, the key sample values here, again, I've made all these up, so this is just examples. Let's assume that they're 25 for our sample size and a standard deviation of 138. So what would more convincing data than that be? So let's look at this visually. We're trying to be convinced that sigma is higher than 125. Right now we have a sample standard deviation of 138. That's definitely higher than 125. So we have some evidence to support the theory that the population standard deviation is higher than 125. Now, what would be more convincing than the 138 that we have for S? Well, if we had a higher sample standard deviation, like 160, 2000, that would be even more convincing evidence that our standard deviation for the entire population is over 125. So in this scenario, more convincing data is a sample standard deviation that's greater than the one we have, 138. Remember though, that is only the first half of determining left-right two-tailed. Once we know what more convincing data is, the second step is to look at the equation and see how it would react if we were to have more convincing data or a greater value for S than the 138 we have now. So, assuming that our population was normally distributed, here's our standard chi-squared equation that we would be using. And again, the p-values is probably getting our data, so we're going to plug in the n equals 25 and the s equals 138, or more convincing data, we'll deal with that in a minute, assuming the null is true. So the first and the third part of the definition. So we're going to plug in 138 for our sample standard deviation s. We're going to assume sigma is 125 until proven otherwise. N minus 1, 25 minus 1 is 24. So when we plug all that in, our sample standard deviation of 138 equates to a chi-squared score of 29.25. Now, the question is, how would that test statistic, currently it's 29.25, that's the equivalent version of the s equals 138, how would that change if we were to get more convincing data? So let's take a look at the numbers. All right, so if we did, say, 140 for S, that's higher than 138. That would be a little more convincing. 155 would even be more convincing that sigma is bigger than 125. And certainly 300 is way over 125. So if our sample standard deviation was that high, that seems to be very convincing. So what is happening here as our sample values of S are increasing? What is the impact on the test statistic? Well, you'll notice the bigger S gets, the bigger the chi-squared scores get. Okay, so more convincing data in this case with this equation translates to larger chi-squared scores. So in this scenario, right, more convincing data, S gets bigger. That equates to the chi-squared score getting bigger. Bigger chi-squared scores are on the right side of the graph. So our p-value is going to be the probability of getting our test statistic or anything farther to the right, which is why we call this a right-tailed test. So now, let's look at another example of a hypothesis test. For the second example, we're going to test the theory that mu is less than 200, that the mean of the population is less than 200. We'd start by assuming that the mean is 200. So imagine that we have the values n equals 93, x bar is 197, and s is 15. I've made these up so we can do an example. So in this scenario, what would more convincing data be? We're trying to be convinced that mu is less than 200. So we're trying to be convinced that in the entire population, the average is less than 200. So in our sample, our average needs to be less than 200, which it is. It's 197. So 197 is a little smaller than 200. So that's some evidence that the mean mu might be less than 200. Now, what would be more convincing than that? If our sample mean x bar was even smaller, that would be more convincing evidence that mu is less than 200. All right, so in this case, an x bar that's smaller than the 197 we have is what we mean by more convincing data. That's step one. Step two, now look to the equation. Typically, we would be using this equation. Okay? So since our sample size is more than 30, I don't even need to know if my population is normally distributed or not. Okay. We use our data, and assuming the null is true, plug everything in. We would get our test statistic of x bar of 197 turns into a t-score of negative 1.93. So visually, a sample mean of 197 equates to a t-score of negative 1.93. So now we have to look at what would happen to our test statistic. Currently it's negative 1.93. How would that change if we were to get a smaller value for x bar, a more convincing x bar? So let's take a look. Let's plug in some numbers. So 196, a little less than 197, 195, 194. So we're going to do this in small increments. So more convincing values would be a smaller x bar. And as x bar is decreasing here, what's going to happen to the corresponding test statistic? Well, the smaller x bar is, the smaller our z-scores are. So smaller z-scores are where on your graph? So our smaller z-scores are to the left. So our p-value is the probability of getting our test statistic, negative 1.93, or a test statistic that equates to more convincing data, smaller x bars. And as you can see, the smaller x bar gets, the farther off to the left or the smaller the t-score gets. So this is a left-tail test. Okay, so let's look at one more example. So the theory I'm going to test this time is that the proportion is not equal to 0.7. So the proportion or percentage of the population that falls into some category is not 70%. It's something else, anything else. That's the theory we're going to test. So we would start by assuming that 0.7 is the correct proportion or probability. We would need some data. So let's imagine I have a sample of 67 values. So whatever our population is, there's 67 items. And 42 of the 67 fall into the category that we're talking about. So in a Math 115 class, the proportion of underclassmen. 67 students, 42 of them are underclassmen. Something like that. So here, that fraction, 42 over 67, is approximately 0.627. That's definitely less than 0.7. It's definitely not 0.7. So in our sample, we have some evidence that the proportion may not be 0.7. Okay? So in this scenario, what is more convincing data? All right, so currently we have p hat of 0.627. Okay? That's smaller than 0.7. But if I had a sample proportion that was higher than 0.7, like 0.773, that's exactly the same distance off from 0.7. Right? So I would be just as convinced that 0.7 is not the right number with either of these p hats. Right? Because 0.627 is too small, 0.773 is just as much too big. Okay? So if I'm trying to be convinced that p is not 0.7, right, getting these values for p hat, right, and the 0.627 is the one we actually have, right, or getting values for p hat that are farther away from 0.7, either way would be equally convincing to me that 0.7 is the wrong proportion for the population. So here we have two cases to worry about. Right? So more convincing data is simply a p hat that's farther away from 0.7 than the p hat we currently have, 0.627. So let's track this down on a case-by-case basis. So testing a proportion, typically we would use this equation, okay, one you should be familiar with. And when we look at this, we have two cases to consider. We want p hat to be farther away from 0.7 than our p hat currently is. So let's look at the first case. If p hat is really small, so less than the 0.627 we have, well, with the p hat equal to 0.627, that's the small p hat that we have right now, that equates to a z-score of negative 1.3. So visually, p hat of 0.627 equates to a negative 1.3. What would happen if we had an even smaller p hat? So if we were to have a smaller p hat, what would happen to our test statistic? Let's look at some numbers. Let's suppose p hat was 0.6 or smaller at 0.5 or even smaller, 0.4. As our value for p hat goes down, our z-score is going to be going down also. So the smaller p hat is, the smaller the z-scores are with this equation. Again, all this depends on the equation I'm using. So case one says if we have a small p hat, that equates to small z-scores. Visually, that means our z-score would be the one we have or something smaller, something farther to the left. So our p-value will include the left tail because that's the small p hat case. But we also have to worry about the second case. What if p hat was a lot bigger than the 0.7? So again, we've just done the left tail, the p hat small case. If p hat was big, like 0.773, right, then we would get a z-score of 1.3. And again, not surprising because, again, 0.773 and 0.627 are the exact same distance from 0.7. And so with the z-score equation, we have symmetry in the graph. We end up exactly at plus and minus negative 1.3 with those two cases. Okay, so if we had had a p hat that was equally convincing but too high, then we'd have a z-score of 1.3. But what would happen with larger p hats? So let's take a look at the numbers. What happens if p hat is 0.85 or 0.9 or 0.95? In each case, I'm getting more and more convinced that the real probability is not 0.7. And as p hat gets larger and larger, not surprisingly, the z-scores are also getting larger. Okay, so with this equation, larger values for p hat mean larger z-scores. And larger z-scores are farther to the right on the z-graph. So for case two, if we get a big value of p hat, right, if p hat is really large, then we end up with our large z-scores in the right tail. So now we got to put both of these cases together. We looked at what happened if p hat was small, and now what happened if p hat was big. So in both cases, right, when p hat got small, the z-score got small. When p hat got big, the z-score got big. So the probability of getting a p hat that is farther away from 0.7 is equivalent to the probability that the z-score is farther away from 0 in either direction. So this is a two-tailed test. So here's the test we just did. We tested using our standard normal z transformation, and that turned into a two-tailed test. Okay, so I now want to redo this exact same test with all the same information, but a different test statistic equation. So since I'm still trying to be convinced that p hat is not 0.7, I need p hat that's farther away from 0.7 than the one we currently have, which is 0.627. So I'll start by looking at what happens if we have a small p hat. So same thing we did last time. So 0.627 is the p-hat we have. It is less than 0.7, so that's some evidence on the small side. So the corresponding chi-squared score would be 1.7. Again, we're assuming the null is true, so everywhere there was a p in the equation, we plugged in 0.7. Okay. Now, visually, we're saying our sample proportion of 0.627 equates to a chi-squared score of 1.7. The question is, what happens to the chi-squared score if we had an even smaller p-hat? Okay, so let's look at the numbers. And again, I'm going to use the same p-hats we did with the z-score equation. So 0.6 is smaller, 0.5 is even smaller, and 0.4 is smaller yet. And as these p-hats are getting smaller, what is the corresponding response by the chi-squared score? The smaller p-hat gets, the bigger the chi-squared score gets. Okay, so take a look at that. All right? Small p-hats lead to, in this situation, with this equation, bigger chi-squared scores. And that's because of that p-hat minus p squared. P-hat minus p tells you how far above or below p-hat is. So when p-hat gets way below p, when you square that, you get a big outcome. Okay, so if we think about this, the smaller p-hat gets, as p-hat goes to the left, the chi-squared score is actually going to the right. So the right tail is representing the small p-hat case. That takes care of the small p-hat case. Now let's take a look at what happens to our chi-squared scores when p-hat gets really big. Now let's look at the case of what happens if we had a big p-hat. Okay, so we had 0.627. That's a small p-hat. That's the one we actually have. And a little while ago, we determined that 0.773 would be equally convincing on the high side because it's the same distance away from 0.7. Okay, so not surprisingly here, 0.773 for our p-hat gets us the same chi-squared score of 1.7 as the 627 did, right? Because again, both of those numbers are exactly the same distance from p, so p-hat minus p squared will be the same in both cases. So again, p-hat being 0.773 led to a chi-squared score of 1.7. What's going to happen to our chi-squared scores if we had even bigger p-hats? Let's do the math. Okay, so 0.85, that's a bigger p-hat. 0.9, 0.95. So as our p-hats are getting further and further above the 0.7, what's happening to the chi-squared scores? They're getting bigger. So larger values for p-hat turn out to be equivalent to larger chi-squared scores also. So if we had really big values for p-hat, right, we would also end up with these really big chi-squared scores in the right tail. So we have two cases to worry about because we're testing p is not equal to 0.7. We have the case that p-hat is either too small or too big for that to be reasonable. And so we looked at both cases. What happens to the chi-squared score when we had a small p-hat? And what happened to the chi-squared score when we had a big p-hat? And in both scenarios, the farther p-hat got away from 0.7 in either direction, the bigger the chi-squared scores get. Which means our p-value is the area to the right of our test statistic. So this is a right-tailed test. Let's put these last two examples in perspective. So in both cases, we had the same theory to test. Okay. Using the first equation, our standard typical p-hat minus p equals a z-score equation. Small p-hats led to small z-scores. Big p-hats led to big z-scores. So we wanted both the left and right tail of the z-distribution. We were doing a two-tailed test. When we redid the test using a new equation, we still wanted p-hat to either be really small or really large. But in both cases, they gave us outputs of large chi-squared scores. So using the second equation, this is a right tail test. So I want you to pause and think about that for a minute. Our theory, p does not equal 0.7, didn't change. Our evidence, p hat is 42 out of 67, did not change. What changed? Our equation. So right, left, and two tails. It's about both what will convince us the alternative hypothesis is true, and secondly, what happens to your test statistic? How does the equation react if you were to get that more convincing data? Okay, so one last time. Determining if you're doing a right-left two-tailed test is a two-step process. All right, you have to look at your alternative hypothesis. That will tell you what more convincing data is. And then the second step is to check your equation out and say, if p hat got bigger, if x bar got smaller, whatever more convincing data is in the scenario, if that was to happen, how is the equation going to react? And that is how you know if you're doing a right, left, or two-tailed test. If you have any questions about the topics covered in this video, or anything else that's happening in your statistical reasoning class, talk to your instructor, go to their office hours, or take advantage of the free tutoring available in the Math Tutorial Center. Good luck, and go Vols!